Welcome back. Let's read some more. It's still super hot in my living room. 30 degrees. So I'm waiting. The sun is going down. It's soon 5 p.m. So the sun will go down in a few hours. Let's read this V-2, but I made another Dennis video about my tent bag for homeless project. So it's super hot. I need to remember to drink some water because it's super hot in my apartment, and then it will be super hot the whole night. I will cook this hot food, this meatball. I will make potato salad. I will do after I finish reading. Need to remember drinking water. Many people, older people, they forget to drink water. So, but the sun will start to get down in like 2 hours. But it's soon 5 p.m. So that's very good. Then when I finish reading this, it's close to 6 p.m.
V-2 rocket. V-2 redirects here. For other uses, see V-2. The V-2, German, Vergeltungswaffe 2, lit. Vengeance Weapon 2, with the technical name Aggregate 4, A4, was the world's first long-range guided ballistic missile. The missile, powered by a liquid propellant rocket engine, was developed during the Second World War in Nazi Germany as a vengeance weapon and assigned to attack Allied cities as retaliation for the Allied bombings of German cities. The V-2 rocket also became the first artificial object to travel into space by crossing the Kármán line, edge of space, with the vertical launch of MW 18014 on the 20th of June, 1944. Research of military use of long-range rockets began when the graduate studies of Wernher von Braun were noticed by the German army. A series of prototypes culminated in the A4, which went to war as the V-2. Beginning in September 1944, more than 3,000 V-2s were launched by the Wehrmacht against Allied targets, first London and later Antwerp and Liege. According to a 2011 BBC documentary, the attacks from V-2s resulted in the deaths of an estimated 9,000 civilians and military personnel, while a further 12,000 laborers and concentration camp prisoners died as a result of their forced participation in the production of the weapons. The rockets traveled at supersonic speeds, impacted without audible warning, and proved unstoppable. No effective defense existed. Teams from the Allied forces, the United States, the United Kingdom, France and the Soviet Union, raced to seize major German manufacturing facilities, procure the Germans' missile technology, and capture the V-2s launching sites. Von Braun and more than 100 core R&D V-2 personnel surrendered to the Americans, and many of the original V-2 team transferred their work to the Redstone Arsenal, where they were relocated as part of Operation Paperclip. The US also captured enough V-2 hardware to build approximately 80 of the missiles. The Soviets gained possession of the V-2 manufacturing facilities after the war, re-established V-2 production, and moved it to the Soviet Union. Development History, edit. Further information, Wernher von Braun early life, and Wernher von Braun career in Germany. During the late 1920s, a young Wernher von Braun bought a copy of Hermann Oberth's book, Die Rakete zu den Planetenraumen, The Rocket into Interplanetary Spaces. In 1928 a Raketenrummel or rocket rumble fad in the popular media was initiated by Fritz von Opel and Max Valier, a collaborator of Oberth, by experimenting with rockets, including public demonstrations of manned rocket cars and rocket planes. The rocket rumble was highly influential on von Braun as a teenage space enthusiast. He was so enthusiastic after seeing one of the public Opel IK rocket car demonstrations, that he constructed and launched his own homemade toy rocket car in a crowded sidewalk and was later taken in for questioning by the local police, until released to his father for disciplinary action. Starting in 1930, von Braun attended the Technische Hochschule in Charlottenburg, now Technische Universität Berlin, where he assisted Oberth in liquid-fueled rocket motor tests. Von Braun was working on his doctorate when the Nazi Party gained power in Germany. An artillery captain, Walter Dornberger, arranged an Ordnance Department research grant for von Braun, who from then on worked next to Dornberger's existing solid-fuel rocket test site at Kummersdorf. Von Braun's thesis, Construction, Theoretical, and Experimental Solution to the Problem of the Liquid Propellant Rocket, dated the 16th of April, 1934, was kept classified by the German Army and was not published until 1960. By the end of 1934, his group had successfully launched 2 rockets that reached heights of 2.2 and 3.5 kilometers, 1.4 and 2.2 mi. At the time, many Germans were interested in American physicist Robert H. Goddard's research. Before 1939, German engineers and scientists occasionally contacted Goddard directly with technical questions. Von Braun used Goddard's plans from various journals and incorporated them into the building of the aggregate, a series of rockets, named for the German word for mechanism or mechanical system. After successes at Kummersdorf with the first 2 aggregate series rockets, Braun and Walter Riedel began thinking of a much larger rocket in the summer of 1936, based on a projected 25,000 kilograms, 55,000 pound, thrust engine. In addition, Dornberger specified the military requirements needed to include a 1-ton payload, a range of 172 miles with a dispersion of 2 or 3 miles, and transportable using road vehicles. After the A4 project was postponed due to unfavorable aerodynamic stability testing of the A3 in July 1936, Braun specified the A4 performance in 1937, and, after an extensive series of test firings of the A5 scale test model, using a motor redesigned from the troublesome A3 by Walter Thiel, a 4 design and construction was ordered c. 1938-39. During 28-30 September 1939, Der Tag der Weisheit, English, the Day of Wisdom, conference met at Peenemünde to initiate the funding of university research to solve rocket problems. By late 1941, the Army Research Center at Peenemünde possessed the technologies essential to the success of the A4. The 4 main technologies for the A4 were large liquid fuel rocket engines, supersonic aerodynamics, gyroscopic guidance and rudders in jet control. At the time, Adolf Hitler was not particularly impressed by the V-2. He opined that it was merely an artillery shell with a longer range and much higher cost. During early September 1943, Braun promised the Long-Range Bombardment Commission that the A-4 development was practically complete /concluded, but even by the middle of 1944, a complete A-4 parts list was still unavailable. Hitler was sufficiently impressed by the enthusiasm of its developers, and needed a wonder weapon to maintain German morale, so he authorized its deployment in large numbers. The V-2s were constructed at the Mittelwerk site by prisoners from Mittelbau-Dora, a concentration camp where 20,000 prisoners died. In 1943, the Austrian resistance group including Heinrich Meyer managed to send exact drawings of the V-2 rocket to the American Office of Strategic Services. Location sketches of V-rocket manufacturing facilities, such as those in Peenemünde, were also sent to the Allied General Staff in order to enable Allied bombers to perform air strikes. This information was particularly important for Operation Crossbow and Operation Hydra, both preliminary missions for Operation Overlord. The group was gradually captured by the Gestapo and most of the members were executed. Technical details, edit. Layout of a V-2 rocket. The A-4 used a 75% ethanol /25% water mixture, B-Stoff, for fuel and liquid oxygen, LOX, A-Stoff, for oxidizer. The water reduced the flame temperature, acted as a coolant by turning to steam and augmented the thrust, tended to produce a smoother burn, and reduced thermal stress. Rudolf Hermann's supersonic wind tunnel was used to measure the A-4's aerodynamic characteristics and center of pressure, using a model of the A-4 within a 40 square centimeter chamber. Measurements were made using a Mach 1.86 blowdown nozzle on the 8th of August, 1940. Tests at Mach numbers 1.56 and 2.5 were made after the 24th of September, 1940. At launch the A-4 propelled itself for up to 65 seconds on its own power, and a program motor held the inclination at the specified angle until engine shut down, after which the rocket continued on a ballistic free-fall trajectory. The rocket reached a height of 80 kilometers, 50 mi, or 264,000 feet after shutting off the engine. The fuel and oxidizer pumps were driven by a steam turbine, and the steam was produced by concentrated hydrogen peroxide, T-Stoff, with sodium permanganate, Z-Stoff, catalyst. Both the alcohol and oxygen tanks were in aluminum-magnesium alloy. The turbo pump, rotating at 4,000 rpm, forced the alcohol and oxygen into the combustion chamber at 125 liters, 33 US gallons, per second, where they were ignited by a spinning electrical igniter. Thrust increased from 8 tons during this preliminary stage whilst the fuel was gravity-fed, before increasing to 25 tons as the turbo pump pressurized the fuel, lifting the 13.5-ton rocket. Combustion gases exited the chamber at 2,820 degrees Celsius, 5,100 degrees Fahrenheit, and a speed of 2,000 m, 6,600 feet, per second. The oxygen-to-fuel mixture was 1.0:0.85 at 25 tons of thrust, but as ambient pressure decreased with flight altitude, thrust increased until it reached 29 tons. The turbo pump assembly contained 2 centrifugal pumps, one for the alcohol, and one for the oxygen. The turbine connects directly by a shaft to the alcohol pump and through a flexible joint and shaft to the oxygen pump. Hydrogen peroxide converted to steam, using a sodium permanganate catalyst powered the pump, which delivered 55 kilograms, 121 pound, of alcohol and 68 kilograms, 150 pound, of liquid oxygen per second to a combustion chamber at 1.5 mph, 218 psi. Dr. Thiel's development of the 25-ton rocket motor relied on pump feeding, rather than on the earlier pressure feeding. The motor used centrifugal injection, while using both regenerative cooling and film cooling. Film cooling admitted alcohol into the combustion chamber and exhaust nozzle under slight pressure through 4 rings of small perforations. The mushroom-shaped injection head was removed from the combustion chamber to a mixing chamber. The combustion chamber was made more spherical while being shortened from 6 to 1 foot in length, and the connection to the nozzle was made cone-shaped. The resultant 1.5-ton chamber operated at a combustion pressure of 1.52 mph, 220 psi. Thiel's 1.5-ton chamber was then scaled up to a 4.5-ton motor by arranging 3 injection heads above the combustion chamber. By 1939, 18 injection heads in 2 concentric circles at the head of the 3 mm, 0.12 in, thick sheet steel chamber, were used to make the 25-ton motor. The warhead was another source of trouble. The explosive used was amatol 60/40 detonated by an electric contact fuse. Amatol had the advantage of stability, and the warhead was protected by a thick layer of glass wool, but even so it could still explode during the re-entry phase. The warhead weighed 975 kilograms, 2,150 pound, and contained 910 kilograms, 2,010 pound, of explosive. The warhead's percentage by weight that was explosive was 93%, a very great percentage when compared with other types of munition. A protective layer of glass wool was also used for the fuel tanks so the A4 did not have a tendency to form ice, a problem which plagued other early ballistic missiles such as the balloon tank design SM-65 Atlas which entered U.S. service in 1959. The tanks held 4,173 kilograms, 9,200 pound, of ethyl alcohol and 5,553 kilograms, 12,242 pound, of oxygen. The V-2 was guided by 4 external rudders on the tail fins, and 4 internal graphite vanes in the jet stream at the exit of the motor. These 8 control surfaces were controlled by Helmut Holzer's analog computer, the Misssteuert, via electrical hydraulic servometers, based on electrical signals from the gyros. The Siemens Vertikant Lev 3 guidance system consisted of 2 free gyroscopes, a horizontal for pitch and a vertical with 2 degrees of freedom for yaw and roll, for lateral stabilization, coupled with a Piger accelerometer, or the Walter-Woman radio control system, to control engine Q-taff at a specified velocity. Other gyroscopic systems used in the A4 included Kresel-Durate's SG-66 and SG-70. The V-2 was launched from a pre-surveyed location, so the distance and azimuth to the target were known. Fin 1 of the missile was aligned to the target azimuth. Some later V-2s used guide beams, radio signals transmitted from the ground, to keep the missile on course, but the first models used a simple analog computer that adjusted the azimuth for the rocket, and the flying distance was controlled by the timing of the engine cut-off, Bremsglas, ground controlled by a Doppler system or by different types of onboard integrating accelerometers. Thus, range was a function of engine burn time, which ended when a specific velocity was achieved. Just before engine Q-taff, thrust was reduced to 8 tons, in an effort to avoid any water hammer problems a rapid Q-taff could cause. Dr. Friedrich Kirchstein of Siemens of Berlin developed the V-2 radio control for motor cutoff, German, Bremsglas. For velocity measurement, Professor Woman of Dresden created an alternative of his Doppler tracking system in 1940-41, which used a ground signal transponded by the A4 to measure the velocity of the missile. By the 9th of February, 1942, Peenemünde engineer Gerd de Beek had documented the radio interference area of AV2 as 10,000 meters, 33,000 feet, around the firing point, and the first successful A4 flight on the 3rd of October, 1942, used radio control for Brennsklas. Although Hitler commented on the 22nd of September, 1943 that it is a great load off our minds that we have dispensed with the radio guiding beam, now no opening remains for the British to interfere technically with the missile in flight. About 20% of the operational V-2 launches were being guided. The Operation Penguin V-2 offensive began on the 8th of September, 1944, when Leonid Versuch's Battery No. 444, English, Training and Testing Battery 444, launched a single rocket guided by a radio beam directed at Paris. Wreckage of combat V-2s occasionally contained the transponder for velocity and fuel QTAF. The painting of the operational V-2s was mostly a ragged-edged pattern with several variations, but at the end of the war a plain olive-green rocket was also used. During tests the rocket was painted in a characteristic black and white chessboard pattern, which aided in determining if the rocket was spinning around its longitudinal axis. The original German designation of the rocket was V-2, unhyphenated exactly as used for any Third Reich-era second prototype example of an RLM-registered German aircraft design, but US publications such as Life magazine were using the hyphenated form V-2 as early as December 1944. Testing, edit. See also, list of V-2 test launches. For a description of a test explosion, see Test Stand 7. The first successful test flight was on the 3rd of October, 1942, reaching an altitude of 84.5 kilometers, 52.5 miles. On that day, Walter Dornberger declared in a meeting at Peenemünde, "This 3rd day of October, 1942, is the first of a new era in transportation, that of space travel." 2 test launches were recovered by the Allies, the Bakiba rocket, the remnants of which landed in Sweden on the 13th of June, 1944, and one recovered by the Polish resistance on the 30th of May, 1944 from the Blizna V-2 missile launch site and transported to the UK during Operation Most 3. The highest altitude reached during the war was 174.6 kilometers, 108.5 miles, the 20th of June, 1944. Test launches of V-2 rockets were made at Peenemünde, Blizna and Tuchola Forest, and after the war, at Cuxhaven by the British, White Sands Proving Grounds and Cape Canaveral by the US, and Cape Estinga by the USSR. Various design issues were identified and solved during V-2 development and testing. 1. To reduce tank pressure and weight, rapid flow turbo pumps were used to increase pressure. 2. A short and lighter combustion chamber without burn-through was developed by using centrifugal injection nozzles, a mixing compartment, and a converging nozzle to the throat for homogeneous combustion. 3. Film cooling was used to prevent burn-through at the nozzle throat. 4. Relay contacts were made more durable to withstand vibration and prevent thrust cut-off just after liftoff. 5. Ensuring that the fuel pipes had tension-free curves reduced the likelihood of explosions at 1,201,800 m, 4,0006,000 foot. 6. Fins were shaped with clearance to prevent damage as the exhaust jet expanded with altitude. 7. To control trajectory at liftoff and supersonic speeds, heat-resistant graphite vanes were used as rudders in the exhaust jet. Airburst problem, edit. Through mid-March 1944, only 4 of the 26 successful Blizna launches had satisfactorily reached the Sonaki target area due to in-flight breakup, Luftsilge, on re-entry into the atmosphere. As mentioned above, one rocket was collected by the Polish Home Army, with parts of it transported to London for tests. Initially, the German developers suspected excessive alcohol tank pressure, but by April 1944, after 5 months of test firings, the cause was still not determined. Major General Rossmann, the Army Weapons Office Department Chief, recommended stationing observers in the target area. See May /June. Dornberger and von Braun set up a camp at the center of the Poland target zone. After moving to the Heidekraut, SS Mortar Battery 500 of the 836th Artillery Battalion, motorized, was ordered on the 30th of August to begin test launches of 80-sleeved rockets. Testing confirmed that the so-called tin trousers, a tube designed to strengthen the forward end of the rocket cladding, reduced the likelihood of air bursts. Production, edit. Main article, Mittelwerk. On the 27th of March, 1942, Dornberger proposed production plans and the building of a launching site on the Channel coast. In December, Speer ordered Major Tom and Dr. Steinhoff to reconnoiter the site near Wotten. Assembly rooms were established at Peenemünde and in the Friedrichshafen facilities of Zeppelin Works. In 1943, a third factory, Reichswerk, was added. On the 22nd of December, 1942, Hitler signed the order for mass production, when Albert Speer assumed final technical data would be ready by July 1943. However, many issues still remained to be solved even by the autumn of 1943. On the 8th of January, 1943, Dornberger and von Braun met with Speer. Speer stated, "As head of the TOT organization, I will take it on myself to start at once with the building of the launching site on the Channel coast," and established an A4 production committee under Dijen Kolb. On the 26th of May, 1943, the Long-Range Bombardment Commission, chaired by AEG Director Peterson, met at Peenemünde to review the V-1 and V-2 automatic long-range weapons. In attendance were Speer, Air Marshal Erhard Milch, Admiral Karl Dornitz, Colonel General Friedrich Frum, and Karl Saw. Both weapons had reached the final stage of development, and the Commission decided to recommend to Hitler that both weapons be mass-produced. As Dornberger observed, the disadvantages of the one would be compensated by the other's advantages. On the 7th of July, 1943, Major General Dornberger, von Braun, and Dr. Steinhoff briefed Hitler in his Wolfslehre. Also in attendance were Speer, Wilhelm Keitel, and Alfred Jodl. The briefing included von Braun narrating a movie showing the successful launch on the 3rd of October, 1942, with scale models of the Channel coast firing bunker, and supporting vehicles, including the Mailer away gen. Hitler then gave Peenemünde top priority in the German armaments program, stating, "Why was it I could not believe in the success of your work? If we had had these rockets in 1939, we should never have had this war." Hitler also wanted a second launch bunker built. Saw planned to build 2,000 rockets per month, between the existing 3 factories and the Nordozen Mittelwerk factory being built. However, alcohol production was dependent upon the potato harvest. A production line was nearly ready at Peenemünde when the Operation Hydra attack occurred. The main targets of the attack included the test stands, the development works, the pre-production works, the settlement where the scientists and technicians lived, the Trassenheide camp, and the harbor sector. According to Dornberger, serious damage to the works, contrary to first impressions, was surprisingly small. Work resumed after a delay of 4 to 6 weeks, and because of camouflage to mimic complete destruction, there were no more raids during the next 9 months. The raid resulted in 735 lives lost, with heavy losses at Trassenheide, while 178 were killed in the settlement, including Dr. Thiel, his family, and Chief Engineer Walther. The Germans eventually moved production to the underground Mittelwerk in the Konstein, where 5,200 V-2 rockets